800,000 galaxies in one image, not a simulation, not a computer-generated model of what the universe might look like. An actual photograph, or rather a catalog of actual photographs, of 800,000 real galaxies, each one a gravitationally bound system of billions of stars spread across a patch of sky roughly the size of 3 full moons. Published today, May 11th, 2026, in the Astrophysical Journal by an international team led by the University of California, Riverside. This is the largest and most detailed map of the universe's cosmic web ever made. It stretches back nearly 13 billion years, to a time when the universe was barely 1 billion years old. It reveals structures that were invisible before this telescope existed. It is challenging the models cosmologists have used to explain the universe for decades, and it contains a map of something that cannot be seen, cannot be touched, and has never been directly detected. Dark matter, the invisible scaffolding that built everything. Let us start with what the cosmic web actually is, because this is one of those concepts that sounds abstract until you understand it, and then it changes how you see the night sky forever. Look up on a clear night, and the universe appears random. Stars scattered in every direction, no obvious pattern, no structure, just points of light spread across blackness in what seems like chaos. That appearance is wrong. On scales far larger than anything visible to the naked eye, across hundreds of millions and billions of light years, the universe is profoundly structured. Galaxies do not sit randomly in space, they cluster into groups. Groups cluster into clusters, clusters link into superclusters, and those superclusters trace long, thin filaments of matter that stretch across the cosmos, threads billions of light years long, connecting at dense nodes where the most massive galaxy clusters sit, and surrounding vast, nearly empty regions called voids, where almost nothing exists. From a distance, great enough to see it all at once, this structure looks like a three-dimensional spiderweb, or the neural network of a brain, or the mycelial network of a forest. Scientists call it the cosmic web, and it is the largest structure in the known universe. The cosmic web was predicted theoretically in the 1970s and 1980s, when cosmologists using the first large-scale computer, simulations of the universe found that gravity, dark matter, and the initial conditions of the Big Bang naturally produced this filamentary structure over billions of years. It was first observed directly using ground-based galaxy surveys in the 1990s. But until the James Webb Space Telescope, the observations that confirmed the cosmic web's existence were limited in resolution, limited in depth, and limited in the era of the universe they could probe. Hubble could see far. Webb sees farther in more detail at more wavelengths, with sensitivity that Hubble could not approach. And what Webb has now revealed about the cosmic web, in the Cosmos Web survey published today, is a level of detail that is already forcing cosmologists to update their models. The Cosmos Web survey was the largest general observer program ever selected for JWST. It was designed from the start with one specific goal: to map the cosmic web across cosmic time. The survey covered a contiguous area of sky about the size of 3 full moons, which sounds small until you understand what JWST sees within it. Hubble peered at a similar region of sky for its ultra-deep field and found approximately 10,000 galaxies. The Hubble image, printed on a standard piece of paper, would show all 10,000. The Cosmos Web image at the same depth would have to be printed as a 13-foot by 13-foot mural to contain all 800,000 galaxies it resolved. That difference, 10,000 versus 800,000 galaxies in the same stretch of sky, reflects the difference between what 2 generations of space telescope can see. Hossein Hatamnia, a graduate student at UC Riverside and Carnegie Observatories, who led the study, described the result in terms that every astronomer in the collaboration has echoed. For the first time, he said, it is possible to study the evolution of galaxies in cluster and filamentary structures across cosmic time, all the way from when the universe was 1 billion years old up to the nearby universe. Before this survey, that statement was aspirational. After today, it is a description of actual data that anyone in the world can download and analyze. The entire Cosmos Web catalog was released publicly alongside the paper. Raw images, processed catalogs, redshift measurements, galaxy classifications. The data democratization is intentional. Professor Caitlin Casey of UC Santa Barbara, who co-leads the Cosmos collaboration, said directly that the best science happens when everyone thinks about the same data set differently, and it is not just for one group to figure out the mysteries. Now let us talk about what is actually inside this map. Because the findings are not just visually spectacular, they are scientifically disturbing in the best possible sense. The first finding is what the map reveals about the cosmic web structure in the early universe. Before JWST, cosmologists believed that the first billion years of the universe were a relatively featureless era. The Big Bang had happened, matter was spreading outward, and gravity was only beginning to pull things into the clumps that would eventually become galaxies. The large-scale structure of the cosmic web, the filaments, the nodes, the voids, was expected to be sparse and poorly defined in that early epoch. What Cosmos Web shows is different. The cosmic web was more structured, more developed, and more complex at early times than most models predicted. Bahram Mobasher, a distinguished professor of physics and astronomy at UCR who supervised Hatamnia's work, said the jump in depth and resolution from Hubble to Webb is truly significant, and that what used to look like a single structure now resolves into many, with details that were previously smoothed away now clearly visible. Structures that Hubble saw as one object are 2 or 5 or 10 separate objects at Webb's resolution. The universe's skeleton was already more intricate than previously measured. The second and more unsettling finding involves galaxies that should not exist. Caitlin Casey, reflecting on the Cosmos Web data, posed the question that the entire cosmology community is now wrestling with. The universe was producing too much light too early. It had only about 400 million years to form something like 1 billion solar masses of stars. Standard cosmological models do not know how to make that happen. In the first 500 million years of the universe's existence, Hubble suggested galaxies would be incredibly rare. Gravity needs time to collapse matter into dense enough regions to ignite star formation, and that takes time. JWST finds roughly 10 times more galaxies than expected at these distances. 10 times. And not just more galaxies, different types of galaxies. Massive, luminous, surprisingly mature-looking galaxies at epochs when the universe was only a few hundred million years old, when they should have had no time to build up that mass. Supermassive black holes at redshifts where they should barely have begun forming. The standard cosmological model, called Lambda CDM, has worked remarkably well for decades. It is now being stress-tested by the data JWST is producing in essentially every deep field survey it conducts. The third layer of the Cosmos Web findings involves what may be the most profound revelation of all, the dark matter map that sits beneath and within the galaxy map. Dark matter is the universe's most abundant and most mysterious substance. It is approximately 5 times more prevalent than ordinary matter. The atoms, molecules, stars, and galaxies that make up everything humanity has ever directly observed. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation of any kind in a detectable way. The only evidence for its existence is gravitational. It pulls on ordinary matter, bends light, and shapes the large-scale structure of the universe in ways that ordinary matter alone cannot explain. Remove dark matter from cosmological models, and galaxies do not hold together. Remove it from the universe's history, and the cosmic web does not form. It is the gravitational scaffolding into which everything else falls, and from which everything visible was built. Published in a Nature Astronomy on January 26, 2026, a parallel Cosmos Web study led by Diana Scognamiglio of NASA's Jet Propulsion Laboratory and Gavin Leroy of Durham University produced the highest resolution dark matter map ever made. It uses a technique called weak gravitational lensing, measuring the tiny systematic distortions in the shapes of background, galaxies caused by the gravitational influence of dark matter between those galaxies and Earth. The distortions are small. A galaxy that would be perfectly circular without any intervening mass becomes slightly elliptical. By measuring these tiny ellipticities across hundreds of thousands of background galaxies, the team could reconstruct where the intervening mass, visible and invisible, is located. JWST resolves approximately 129 galaxies per square arc minute of sky. Hubble resolves about 71. Ground-based telescopes resolve fewer than 20. The difference in source density for lensing measurements is directly proportional to the precision of the dark matter map. More resolved background galaxies means more data points. For measuring distortion means a sharper map of what is bending the light. Richard Massey, a physicist at Durham University who co-authored the dark matter study, described the resulting map in terms that go beyond technical vocabulary. He said dark matter is the gravitational scaffolding into which everything else falls and is built into galaxies, and that in this map it is actually possible to see that process happening. Not modeled, not simulated. Seen. The dense regions of dark matter in the map are connected by lower density filaments, forming the same cosmic web pattern that the galaxy map reveals. And in the regions where dark matter is densest, galaxies are most concentrated. The ordinary matter traced the dark matter's lead. Every galaxy in the observable universe, including the Milky Way, including the solar system, including Earth, exists because dark matter pulled ordinary matter into the precise configuration needed for stars to ignite and worlds to form. The side-by-side comparison of the new JWST dark matter map with the original Hubble dark matter map of the same region, made in 2007, roughly 2 decades ago, is one of the most striking scientific comparisons published this year. The Hubble map shows dark matter concentrations as broad, blurry regions. The JWST map shows those same regions resolved into multiple distinct structures. with filaments and density gradients that the Hubble data had smoothed into a single featureless blob. Diana Scognamiglio said seeing the structures match between the old and new data was stunning. But what matters? Scientifically is not the match, but the detail revealed within what used to look like uniform concentrations. Those details are data, and that data constrains theoretical models of what dark matter actually is. And here, the story opens into one of the deepest unsolved problems in all of science. What is dark matter? Cosmologists know it exists because of its gravitational effects. They know approximately how much of it there is. About 27% of the total energy content of the universe, compared to about 5% for ordinary matter and about 68% for dark energy, which is a separate and even more mysterious quantity responsible for the accelerating expansion of the universe. They have an extensive list of candidate particles that could constitute dark matter. Weakly interacting massive particles called WIMPs, axions, sterile neutrinos, primordial black holes. Decades of direct detection experiments deep underground, designed to catch the rare interaction of a dark matter particle with an atomic nucleus, have found nothing definitive. Particle accelerators, including the Large Hadron Collider, have not produced dark matter particles. And yet, the gravitational evidence for dark matter's existence is overwhelming. The JWST map does not identify what dark matter is, but it maps where it is with unprecedented precision, and the more precisely it is mapped, the more constrained the theoretical models for what it could become. The cosmological implications of the Cosmos Web results are still being absorbed by the field. The paper describing the cosmic web mapping was published today. The dark matter study appeared in January 2026. Both are products of a survey that has been years in design and 2 years in data collection. Gavin Leroy, who co-led the dark matter study, described it as a key first step for all future knowledge about dark matter, and noted that work is already underway to produce a three-dimensional version of the dark matter map, adding the depth dimension to what is currently a two-dimensional projection. The European Space Agency's Euclid telescope, which launched in 2023 and has been conducting its own large area sky survey, will extend dark matter mapping across a much wider swath of sky, trading JWST's extraordinary resolution for enormous area coverage. NASA's Nancy Grace Roman Space Telescope, expected to launch later in 2026, will provide complementary observations, combining wide coverage with resolution between Hubble and Webb. The Vera C. Rubin Observatory in Chile, which released its first images in June 2025, will add a ground-based perspective to the same scientific questions. The era these instruments are inaugurating has been called a golden age of cosmology. That phrase gets used often enough that it risks losing meaning, but the Cosmos Web results published today make the case for it concretely. A single survey, one program on one telescope, covering 3 moon widths of sky, has produced 800,000 galaxies spanning nearly all of cosmic time, the most detailed dark matter map ever made. Evidence of galaxies that should not exist under the standard cosmological model, and a direct visual record of the process by which dark matter's gravity built the structure of the universe from which everything we know emerged. What used to require the combined effort of ground and space observatories over decades, JWST accomplished in 255 hours of observation time, covering an area of sky smaller than a thumbnail held at arm's length. The universe is not random. It is structured. Its skeleton is dark matter. Its flesh is gas and stars and galaxies pulled into filaments and clusters and nodes by gravity working over 13.8 billion years. And today, for the first time in the history of astronomy, we have a map of that skeleton detailed enough to see individual bones. What we do with that map, what questions it lets us ask that we could not ask before, what answers it delivers to questions we have been asking for decades, is the story that the next few years of cosmology will write. The telescope is still observing. The data keeps coming. And every time JWST opens its golden eye on another patch of sky, the universe reveals something it has been hiding since before the Earth existed. 800,000 galaxies, 13 billion years of cosmic history, one telescope, and a map that has already changed what we know about the universe we live in on the day it was published.